This podcast is on a combination of things, specifically the perfect gas law, titration, empirical and molecular formulas, and atom economies. It is an extension of stoichiometry that you have done in grades 9 and grades 10. The assessment criteria for this unit is to know the perfect gas or the ideal gas equation and be able to apply it. That's what it's called in the West. You'll need to understand the purposes of titration, calculate how much in an actual laboratory setting a titration needs to neutralize the acid or the base, and you will also have to carry out experimental opportunities in titration. You also need to know how to make calculations for the determination of empirical and molecular formula of a substance, and as I said before, discuss atom efficiency. More of all of these will be discussed in class, but this covers what you will see for assessment criteria. On the left-hand side of this slide, you see the perfect or ideal gas equation. PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature in Kelvin. Now, depending on who is doing the calculations, there are many different representations for the gas constant. They are all the same, but they differ by what units the other information is in. And you can see that table of values that are all the same universal gas constant, but the differences when the pressure for, say, is in atmospheres rather than kilopascals. Let's look at an example of an ideal gas law. Look at the example on the right. Look at each of the steps. If you have a problem with that calculation, ask your teacher in class. This is a straightforward solution of the temperature when the pressure, volume, and number of moles is available. Titration is also an important part of our study in grades 11 and 12. It is used as a basis for experimental understanding of acids and bases. It's also the basis of many of our testing protocols in the community in water testing and other kinds of testing for specific ions. And it's an important part of the end of year testing regimen. Out of the 3 or 4 questions that you have on paper 3 of the practical, 1 is always a titration. Let's look at this video that describes the entire process as well as some definitions that you should know in English in order to be able to do titrations on the practical on paper 3.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, we will be discussing the proper titration technique using the complete single burette assembly kit available from Carolina Biological Supply Company. This is the first in a 2-part video series on titration. The purpose of a titration is to quantitatively determine the concentration of an unknown solution, commonly called the titrand or analyte, by adding a volume of a chemical with a known concentration called the titrant. To mark the endpoint of a titration, an indicator is added to the analyte. Let's review some of the equipment that's needed for a titration. Carolina's complete burette assembly contains the basic equipment to get you started, including a burette, ring stand, and a burette clamp. A burette is a long, narrow, graduated tube used to add titrant. It has a stopcock to regulate the flow of liquid. Notice that the markings on the burette go from lowest at the top to highest at the bottom. The ring stand and burette clamp are used to mount and secure your burette. Other materials you will also need include a small funnel to help you fill the burette, a 125 milliliter Erlenmeyer flask, which works best for titrations. The shape of the flask allows for more vigorous swirling than a beaker or other glassware and minimizes spill hazards. A volumetric pipette and pipette bulb to transfer a known volume of analyte to the flask. A wash bottle filled with deionized water, a beaker or flask of titrant and of analyte, indicator selected for your reaction, a reading card to help read the meniscus, and a sheet of white paper to help visualize the endpoint. To prepare your burette for the titration, it is good laboratory practice to rinse your burette thoroughly with deionized water, then with a small amount of titrant. After each rinse, open the stopcock to allow the liquid to drain out the bottom. If there is a lot of liquid clinging to the walls of the burette, then thoroughly clean your burette and repeat the rinse process. The accuracy of this technique is dependent on the titrant flowing into the flask and not sticking to the walls of the burette. Mount the burette in the clamp, making sure it is positioned vertically and there is enough room to position your flask underneath the tip. Check to see that the stopcock is in the closed position. Insert the funnel into the top of the burette and fill with titrant almost to the top. Filling exactly to the 0 mark is not necessary, but you do need sufficient titrant to complete the reaction. Check the column for air bubbles and gently tap to free them from the side walls. Remove the funnel. Place the Erlenmeyer flask under the tip and open the stopcock to allow a few milliliters of titrant to flow through, releasing any trapped air. Rinse the tip of the burette with water. Empty the liquid into a waste container and thoroughly rinse the flask. It is not necessary to dry the flask. Record your starting volume. It is important to accurately read the volume on the burette. First, note that the liquid forms a concave meniscus because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This burette indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the burette. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the burette requires 2 hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate. Open up the stopcock and allow the titrant to enter the flask quickly. Continuously swirl the flask. As the volume of titrant in the flask increases, the color of the indicator appears, then disappears as you swirl. When the analyte becomes a colored solution, close the stopcock. Record the final volume of the burette. Subtract the initial volume from this final volume to get the estimated volume of titrant needed for this titration. Knowing the volume that is a little past the endpoint, subtract 5 milliliters from that number to get the amount of titrant that can be safely added before a slower addition is required. As the estimate titration shows, a dark-colored solution indicates an excess of titrant has been added. The desired endpoint is a pale, faintly colored analyte. To reduce the risk of passing the endpoint, slow down the addition of titrant when flashes of color begin to appear in the analyte. Adjust the stopcock to slow the flow of titrant to a drop-wise rate. Continue to swirl the flask with one hand and keep the other hand ready to close the stopcock. When you notice the indicator taking longer to fade, close the stopcock. Rinse the tip of the burette with deionized water and swirl the flask. Record the final volume on the burette. If the analyte remains faintly colored, then you have reached the endpoint. If the analyte is still colorless, then repeat these steps. Add a drop, rinse, swirl, and record until a faint color persists. Typically, titrations are performed in triplicate. Use the average volume of the titrant required to reach the endpoint for any calculations. You now know how to properly perform a titration.
You are asked most oftentimes to calculate the amount of acid or the amount of base. In straightforward titration concentration calculations, you can use the formula to the right. There are more extensions of this formula if you are looking now for an empirical formula or a molecular formula. Take a look at what you see here and see if you have any questions. If so, direct them to your teacher. But now we'll talk about something you should be familiar with that I've just mentioned, empirical and molecular formula. Empirical formulas can be found by a simple 4 to 5 step process. The first is to start out with the number of grams of each element given in the problem. Most oftentimes they're given in percentages. And so using and assuming a 100-gram sample, you then calculate the number of moles in a 100-gram sample. Once you have those moles, you divide each mole value by the smallest number of moles calculated. For example, in the blue picture to the right, nitrogen had the smallest number of moles. So you would divide that number into the other two numbers. It looks like the number of moles of carbon and nitrogen are about the same. And the number of hydrogen happen to be 5 times as great. If you rounded it to the nearest whole number, the ratio indicates the amount of each element in the empirical formula. Now, if you have to find out the molecular formula, you take the amount of the compounds you have and divide it by the empirical formula weight. So in, for example, HCO2, there's 1 OH, 1 carbon, 2 oxygen. So that total 45 is half of the molecular mass you're given. So the formula mass is exactly half of the molecular mass. Hence, H2C2O4. Empirical formula, molecular formula, and titration may be mixed together in one kind of problem. And as we get nearer to the end of your 12th grade year, we'll give you problems that involve all three. The last thing we need to discuss is atom economy. Atom economy is nothing more than a number that gives an indication of how well the reaction you have gives the desired product. The higher the number, the better that reaction is with the conditions to make that product. Atom economy is nothing more than the mass of the atoms in the products divided by the mass of the atoms in the reactants. This is a popular topic when we talk about green chemistry or using the minimum amount of chemicals to make the maximum amount of products. As we had after the first podcast, you'll see these questions to start your thinking. If you need to retake a formative test, please present the answers of these questions to your teacher before you retest.